Hello, scholars. Thank you for returning. Today we're going to be talking about secants, tangents, and segments with inside circles and creating a set of congruency statements around them that's going to allow us to solve for missing pieces. Before we get started with our notes for today, I want to introduce our new sponsor. That's right, today we have a sponsored lesson. Today we have Clorox. If you're looking for a disinfectant, choose one that can't taste any better than pumpkin spice Clorox. Refreshing. All right, let's get to our notes for today. We have segment circles written up along the top here. We're going to be talking about, first off, what happens when chords intersect with one another. Reminder, you can always pause the video, write down anything as you want if you do not want to copy down while I'm just speaking. With our segments and circles, what ends up happening is when we have these two chords crossed one another with inside of our circle, we end up getting portions of our chord divided up. In this particular example here for our circle, which we can call circle L. Circle L is going to be subject to two chords intersecting at point E. When these chords intersect, we end up having a portion or segment CE and ED, AE, and EB. If we had a missing value and wanted to solve for a portion of the chords, we can set up a system of congruency. In our chord segment theorem for today, we're going to state that if two chords intersect inside of a circle, then the product, meaning multiplying the pieces of lengths against one another and then setting them equal to the products of the other chord, we end up being able to find equality between the two. In terms of an example or an equation, we can say, based on our circle here, we can go ahead and look at it as segment AE times segment EB is equivalent to segment CE times segment ED. Nice little statement here. If we wanted to take a look at that in a numerical fashion, we have our circle set down along the bottom here, circle O. We have points F, D, R, and B, C. If we were to set up an equation, we would just be looking at it in this fashion. We'd have dB, which is our unknown. We can set that as an example of x. Point B, BO in our circle for C, we can go ahead and say is a value of 12 equal to FB of 6 times 7. Here, all we would end up doing basically combining 6 times 7 gives us 42, divide our value of 12 over, and set it all equal to x. So right there, we just break down to some of our basic algebra questions from last year. Section here, we're looking at secants and tangent segments. In our diagram that we have down here on the bottom, we're going to be looking at two secants intersecting a circle. If you remember from our definition of a secant, secant's going to be a line or ray that intersects a circle at two separate points, entering and at a point where it either exits and actually carries on or just stops. When we have the secant outside of the circle itself, we're going to refer to this as our external segment. External segment down along the bottom here is going to be CU and CI, but we can just define it as the portion of the secant which exists or lives outside of the circle itself. Similar to our previous section, we're going to look at how that we go about quantifying different secants. Just remember to copy down information at your own speed. In our chord example, we took the different parts and we found the product. We multiplied the different pieces together and then set them equal to the other chord. In this example, we're going to be doing it in a slightly different fashion. With our secant, we're going to add this concept of the external segment into our mathematical theorem. What we're going to do is, if two secants share the same endpoint, as in spot C, we are going to take the length of the entire secant, multiply it by just the external secant, and set that equal to the other in the same fashion. So we'll have, for example, CR, the whole length, or the entire secant, times the external secant, equal to CE, the entire secant, times just that external portion. So we have a slightly different mathematical formula that we're going to do, but in a way they are going to be very similar in that we're just taking the available pieces and setting them equal to each other. This in theory is like another method that we can do proportional statements. We're taking the whole length, we're modifying it by a portion, we're saying equal to a whole length and modifying it by a portion. In our next section, we're going to be looking at a secant and a tangent. We're going to go over a couple examples after we finish up here with these two definitions. But our secant-tangent theorem is somewhat similar. We're doing another proportional statement. But in this particular example, we're going to take the entire length of the secant, say AI. We're going to multiply it by the external value of AL. And with a tangent, we have what's called a tangent segment. It's a piece that goes from the shared point to the little itty-bitty point that touches on the circle. And we're going to square that tangent segment value. So we're taking the whole length times the external length, setting it equal to our tangent segment, which is squared. One thing that might help particular examples is that at least with the tangent, we have one piece. So we're going to be multiplying it essentially by itself. What I'd like to do before we finish up with today's video is show you a couple examples of these two particular ones that we just went over. In this example here, we have another secant tangent example. I've already started to label this out for you. But here we have circle O, and in circle O, we have the entire segment value for our secant as RQ. We have our external segment of RP, and we have our other secant here, RT, and our external value of RS. What you'll notice in our diagram is that at ST we have an unknown value. We have our X value. So we have to take that in consideration in our equation that's here. So we can just start to fill in our values. RQ we're going to say is 9 parentheses plus 11 times our external value of 9 equal to RT, which we're going to quantify as 10 plus X in parentheses times our external value of 10. 9 plus 11 is 20. And on the right-hand side here, we're going to have to use our 10 value and multiply by everything in our parentheses. So first thing I'm going to do here is do 10 times 10, which gives us a value of 100 plus 10x. And that's now going to be equal to 180. And just so you know, this isn't degrees, but length. So we might have units like centimeters or inches, but we have 180 inches or so on the left-hand side. We're now just going to go through it with algebra, break everything down here. We have 80 equal to our 10x value. And then finally, we have an x value of 8. So in this particular example, we're just solving for the value of 8, but theoretically you might have a question along the lines of solve for the length of RT, which therefore you'd have to go in and say 10 plus 8 gives us RT, or 18, for instance, would be equivalent to RT. So little things here and there, little modifications like we've seen throughout all these different types of examples. The next question we're going to look at is our secant tangent. So I have this one drawn up for you. We got points SOPIE, Sophie. It's the name of a famous mathematician during the post-French Revolution era. And what we have here in terms of our equation is we're going to have our secant value, our whole length, times our external, equal to our tangent squared. What that's going to look like here is going to be SI, our whole length value, times our external value, and our tangent value of IE or EI. Now if we just go ahead and start to fill in our values, we have 3 plus 1 times 1 equal to x squared, our unknown value. 3 plus 1, so it's 4. 4 times 1 gives us our x squared. And lastly, we just find our square root of 4. And we get a value of 2 for x. So that's it in terms of these particular examples. What you want to make sure or take away as in these types of questions, if you're having an x value inside your parentheses, you want to make sure that you're multiplying everything times it, just like we saw in our previous example with our 10 plus x times 10, keeping everything in those parentheses. That's pretty much it for this particular section. You'll notice for today you have a set of independent practice questions, exit ticket questions as well too. Just so you know, I set up a 2 different extra credit assignments for you. This week, due tomorrow, which was posted last week, is an extra credit assignment associated with business that you get to help out, a local New York City business, using geometry to increase product revenue. And then going forward, you'll see every week an update to our Delta Math classroom assignment. Just as we had in trimesters 1 and 2, now I have set available reoccurring weekly Delta Math assignment that allow you to get extra credit. Essentially completing one of those activities a week will give you half assignment credit. So every 2 weeks you'll earn, like, say, a free exit ticket or free independent practice, free ed puzzles, things like that. And that'll allow you to help catch up if you've missed anything, or even go above and beyond with what you have now. As always, if you have questions, we got our office hours every Monday, Tuesday, Wednesday, and Thursday from 1:30 to 3:30. Feel free to ask me any questions if you got them. All right, have a nice day.